those ones at least you can rest easy on because they'll get you in one way or another. It's those electives you're counting on. Do you find it worse this year than most years? Because you're earlier, right, than... All right, how you doing? This is super quiet, so I'm going to crank this up a little bit. That should be a little better. Maybe around there. If that's still too quiet online, please let me know. I don't know why it jumps around so much day to day. I don't think I moved this too much, but who knows. So we are in the middle of our unit on polymers, as you're probably well aware. We have a couple of classes left and a couple of units to finish, so I think we're going to be right on track. Another deadline passed for unit assignment 9, I'm going to guess. We're on unit 10 right now, which is polymers, so this one will likely finish today, which means the unit assignment will be due a week from today. Jasmine says the sound is pretty good. That's good to know. Could it be really good, or is this as good as you need it to be? Let me know. I don't want to sound like a robot. I turned up just a tiny bit. So today is also the deadline. So a week from today is the deadline for the link for your video assignment. And I said in the description that if you want to do something besides a video and you have an idea, please come to me with that idea before today. Well, before today ends. Let's say that. Great. So basically, if you want to do something, and please don't email me and just say, I want to do something else, what do you suggest? You need to come with me with an idea. Because if you ask me to provide you an idea, it's going to be make a video, follow the instructions. So yeah, come up with something. I'm sure you can be creative, and you've had it for quite a while to stew on, so hopefully you can come up with something. What else? Not much else. I realized one thing is that, well, I didn't realize it, this has always been the case, but we're not allowed to have any work assigned that's due after the last day of classes, which is the 13th, which is a Tuesday, which is that 2 weeks from last Tuesday? I think it might have been. Yeah. So what that means is any units that we complete, we're going to have to make the due date the 13th between then and now. So what basically that's going to mean is if there's an assignment and you only get 5 days instead of 7 days, I think that's probably acceptable. But if we finish a unit like the day before, I'm not going to make the unit due. Like I'll still have the questions up and available, but those will become optional or something. So I'm not going to set due dates after the 13th into the exam period. Okay, good. I've already received one as a substitute for one of the unit assignments, which were multiple choice questions. So please keep thinking about that. The due date for that is also going to be the last day of class, which is the 13th. So everything is kind of coming together for that last day, the 13th. And the big thing, though, of course, is assignment 2, which is going to be due next Thursday for everyone. Okay, so we're talking about polymers. And we spent quite a bit of time talking about the structure of polymers. Last class, we talked about how polymers have a repeating subunit. And essentially every plastic material that we're familiar with is a polymer, right? It's made up of these small repeating subunits. There's a lot of naturally occurring polymers we looked at, like DNA, starch, cellulose, proteins, things like that. We also looked at a couple of artificial ones. We looked at the early ones, sort of the history of their development. We talked about nylon. We talked about nitrocellulose, bakelite, a few other things like that. And we're going to kind of fast forward right into the modern time and look at the plastics that we are using in the largest amounts, what they're made out of, and maybe a little bit around the specific issues around each one. Because often I think people, the way plastics are often presented in the media or wherever, it's almost like they're presented as a single type of material. It's plastic and then that's it. Where in fact, there's many different types of plastics, all with their associated pros and cons. And they definitely have pros, or else we wouldn't be using them. But they also all have certain cons as well, like any substance, like any chemical, like any material. So we're going to talk a little bit about this. And the very first one we're going to be talking about, this is the #1 plastic in terms of how much is produced, in terms of weight per year. It's called polyethylene. And it's used by taking this small molecule ethylene, which has 2 carbons and 4 hydrogens. And this is a naturally occurring compound that is actually produced by some plants, like bananas. It's a chemical that they produce in order to accelerate the ripening process. But we get ethylene primarily from natural gas deposits. And we can convert this into polyethylene, where each of these kind of corners of the chain here is a CH2. CH2, 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 and so on. And it repeats super long chains. Okay, so they can be thousands, they can be millions of carbons long in an individual chain. So the production of this, going back to 2017, I'm sure that today's production is not that different from this number, was around 100 million metric tons worldwide. It's a huge amount of plastic. It's about 34% of all plastic produced. And we use this for all sorts of different materials. This is very cheap and inexpensive, and typically most disposable plastic is this type. It's used in plastic bags, for example. It's used in packaging. It's used in wrappers, this sort of stuff. It can be used in bottles. The main type of plastic used in pop bottles and water bottles is not polyethylene, though, as we'll see. But, you know, it's this kind of clear, flexible type of material that you're probably very familiar with. Polyethylene actually comes in 2 major types. There's what's called high-density polyethylene. And at the molecular level, you know, we have this kind of chain that we're drawing over here. That chain, you know, is very, very long. If you take that chain and at the molecular level, if it's produced in a way that causes it to pack into this sort of more compact, dense material, where all those chains, you know, that can loop back and forth, but it's kind of tightly packed on itself. This creates a very hard, dense type of plastic material, which we call high-density polyethylene. So it's used to make bottles that are pretty rigid, pretty firm, and kind of like hard plastic toys, things like this. You can also have low-density polyethylene, which is the same type of material, but it has these kind of branches on the chains, these branching chains as it goes out, almost like roots of a tree. And because these chains are branched, what happens is they don't pack together very well. They don't pack as tightly or as compactly. They make a material that's much more flexible and much less rigid. So what we end up with is, you know, if you want a plastic that is more flexible, like you would want if you're wrapping something or making a bag or something like that, you would want to use low-density polyethylene. And so the difference in their physical properties is just a result of how those chains exist at the molecular level and how they pack together. So these are recyclable. They both have 2 different recycling codes. The high-density polyethylene is recycling code 2, and the low-density is recycling code number 4. The number 2 plastic is polypropylene. And polypropylene is actually very, very similar in structure to polyethylene. It just has these little kind of short side branches on every second carbon along the chain. Okay, it's made from a compound called propylene, which itself can be made from propane. And propane we get from natural gas as well. Natural gas, when you take it out of the ground, is mostly methane, but it contains other things as well. So you can strip off the propane, use it in your barbecue, or you can turn it into propylene, which makes polypropylene plastic. So these all come from hydrocarbon fuels. It's got recycling code number 5. So if you're wondering what all these numbers are on the recycling codes, it tells you the type of plastic, which if you're sorting them, you'd want to know that. It produces a similar type of material. It's very rigid. Notice that the chain, by the way, is all carbons and hydrogens, so it's very non-polar. And so for this reason, plastics like polyethylene and polypropylene are very water resistant, waterproof. So you could make a container that would hold water, and the plastic itself is not going to let it seep through. It's not going to dissolve itself or weaken the container or anything like that. We got about 74 million metric tons produced a year. It's very chemically resistant, very flexible, very durable. And so, you know, if you're familiar with this kind of chair, those plastic chairs, that's typically the material where it's pretty durable. It's flexible enough that if you sat on it, it's not going to crack or break, hopefully. And it's also used a lot in plumbing. It's used for pipes that are drain pipes. And that way, because it's chemically resistant, you can have chemicals like drain cleaners and stuff like that run through and not destroy your pipes when they go through. So it's good for that purpose as well. This is a paper that was published quite a while ago now, I guess 2008, in the journal Science. And if you remember the journal Science, one of our very first lectures, we talked about this journal as being one of the top 2 journals in the whole, area of science altogether, the other one being Nature. So this is a very top journal. And the reason I wanted to highlight this one is because of this, number 5 here, Department of Chemistry, Acadia University, Wolfville. The professor is Dr. Amitabh Jha, and he was a participant in this paper. And what this paper was talking about was bioactive contaminants leach from disposable laboratory plasticware. And what this is about is when you work in a lab, you have to buy materials to do your work and your experiments and your assays and things like that. And there are companies that produce plastic containers that are meant to be disposable, so you use them once and you throw them away. That prevents cross-contamination. So if you want to do, say, 10 assays, you're not risking contaminating your second one by using it in the same glassware as your first one. So they make this disposable plastic laboratory glassware. And so this was an actual test where they were buying this stuff, they were running assays, and what they were finding is like really, really weird results. And what they eventually found out or discovered was the problem is this disposable laboratory plasticware that was designed for this purpose had other compounds either in the plastic or on the surface of the plastic by design, by manufacture, that was interfering with the assays that they were doing. And they found that these results were screwing up their assays, which is kind of crazy considering that this labware was designed for this purpose. And Dr. Jha's contribution to this is he synthesized in his lab pure samples of all of the what are called slip agents that they add to the plastic. And he made pure samples and they tested them at different concentrations in each of these assays. And sure enough, these compounds were screwing up the assays. And so this paper was really published as a warning to anybody who are running these types of assays to really be careful what sort of containers you're running your assays in, because you might be getting really wacky results that have nothing to do with the actual science. It's because of these additional materials. And the reason I like to bring this up here is because when we talk about plastics like polyethylene, polypropylene, or whatever, it's generally speaking not just pure plastic material. There's often other things that are added either integrated with the plastic or coating the surface of the plastic. In this case, they're called slip agents. Causes the plastic to become lubricated. which makes it easy if you're going to put like a cap on a vial or something like that. The cap would slip in easy, as opposed to pure plastic that wouldn't have that in there. So that's just one type of additive that can be put into plastics. And we're going to be looking at this in much more detail in a few minutes. When we focus in on our plastic number 3, which is polyvinyl chloride, which is produced around 40 million tons per year. So, you know, it's a lot less than polyethylene, which is around 100 million tons, but certainly quite a bit. It gets recycling code number 3 and is sometimes just abbreviated as V. And V in this case stands for vinyl. So vinyl plastic is this one, polyvinyl chloride. It's taking a molecule, which is vinyl chloride, which is the monomer. It's attaching many of these in a long chain. So you have, again, this carbon-carbon chain, which looks like polyethylene, except every second carbon has a chlorine attached. So again, these structures of these most produced plastics, polyethylene, polypropylene, and now polyvinyl chloride, have very, very similar structures, right? They all have that same long carbon chain with just different kind of side groups attached. Polyvinyl chloride is used for all sorts of things. It's a very, very versatile plastic, very rugged, very durable, like I guess many other plastics. And you see this a lot in home construction. It's a very common material for construction, for pipes, for example. Most drain pipes are PVC. Here's a picture of a house that a friend of mine was actually considering purchasing in Wolfville a number of years ago. And the reason I have this here is just to kind of point out how much polyvinyl chloride you're looking at kind of all the time without even realizing it. So the siding on this house is vinyl siding. Vinyl siding is polyvinyl chloride. Typically, the shutters would be made out of polyvinyl chloride, as well as kind of the framing around the windows. Older windows are wooden, modern ones, PVC. This decking material, these kind of vertical slats, if you see those and they're plastic, it's probably PVC. And also gutters. Gutters are made out of PVC. You can get aluminum ones too, but if they're plastic, it's PVC. What else? Well, probably a lot of the pipes that are underground here going into the house and out of the house, they're probably PVC as well. So there's a huge amount of PVC just in sort of every, well, I guess a house is like an everyday object, but you know what I mean. Very, very common plastic. Now, PVC comes in different forms that are actually very, very different in terms of their properties. So this rubber ducky, I'm sure you're familiar with how those feel. They're very soft, they're squishy, very, very flexible. That's PVC. Also, vinyl records are also PVC. And if you hold these one in each hand, they couldn't be more different from each other in terms of their material properties. You know, the records on the left are very rigid, very hard, very brittle. You know, if you dropped one on a hard surface, it's likely to crack or shatter. Whereas the guy on the right here, totally different. You know, you could not shatter that. Unless you maybe froze it with liquid nitrogen, but we're not doing that. How can these be the same material? How can these be the same substance? And the answer to this question is, what are the additives that are put into this substance? Because neither of these substances are pure PVC, pure polyvinyl chloride. Something else is added to them for some reason. And what's added to the one on the right is something called plasticizer. And plasticizer is small molecules that will integrate themselves in between the strands of the chains. So remember with polyethylene, we said if the chains can densely pack together, it makes a hard, rigid material. But if they branch out, then it doesn't become rigid. Well, what the plasticizers do is they kind of get in between the chains, the long chains of the polymer, the plastic, and they make it so they don't pack together so nice and dense anymore. It makes the plastic flexible, and it's this material that's added which gives it this property. So phthalates are a class of compounds which Several of you actually chose as topics for assignment 1, which is interesting to see, so this might sound familiar. Not polystyrene, PVC. And it makes it softer, more pliable. So any material you think of as vinyl that is soft and flexible has this type of plasticizer in it. So not just a rubber ducky, but like a vinyl shower curtain. It's also very flexible. If you wear clothes that are vinyl, like, you know, vinyl pants or things like that, that's very flexible as well. Fake leather, pleather, it's that's also typically vinyl. This was used to be more popular than I haven't seen much of this lately, but when you have old furniture and the furniture is sort of like a fake leather look to it, and it's kind of this plasticky material, often doesn't even look like leather. It could be bright orange or bright blue. That's often vinyl as well that has this phthalates in it. Take the phthalates out and you get a hard, rigid material that you'd use for gutters or albums, like you see on the slides here. So Barbie dolls are made out of PVC. And if you've played with Barbie dolls before, and you kind of realize how flexible like the legs and arms are, that's got a certain amount of plasticizer in it. And the addition of the plasticizer to the plastic makes it flexible. It also allows migration of chemicals through the plastic. And I remember when my girls were really young and we'd go to the dollar store and would sometimes get these little dolls. Like they weren't Barbies, but they were some knockoff. And sometimes you'd get one and it'd be really sticky. Or sometimes if you have like a doll and you leave it outside or leave it in the heat, it gets really sticky. What that is the plasticizer, the phthalates, migrating out to the surface and making the surface kind of gummy and sticky. You see that a lot actually with those pens with like a rubber grip. And it's not rubber, it's probably PVC. And then they get sticky after a while. And that's because the phthalates that are in there, the plasticizers migrate out of the plastic over time. So Barbies, this is the OG. It's the original Barbie from sometime in the 1960s. Looked like that with that exact suit and everything. And she actually came with earrings. It's funny, you end up sometimes down like an internet rabbit hole. And I don't know why, but I was reading about people that collect Barbie dolls. I don't actually have any, so I don't have a collection of these myself. But the earrings were made out of copper metal, which looks kind of like gold, I guess, and it's a cheap thing. But what happens to copper metal, and we sometimes put solid to make it copper, is it can react with oxygen and turn into copper 2+. It makes copper ions, which are green. And if you have an old Barbie from the 60s and it had the earrings and the earrings were left in, often what you see on the Barbie is this big green patch around the ear. And that's oxidized copper from the earrings that have started in the ear and then migrated out because the plasticizer that's in there allows things like copper to migrate through. That migration would be very slow. It would require decades for it to move through to that kind of distance. But apparently if you're a collector of these dolls, that green patch on the ear, which is a very common affliction, dramatically reduces the value. And so I guess the best thing you could have done, back if you have a time machine and went back to the 1960s, is take the earrings out and store them separately. Or store the entire thing in an airtight container with no oxygen in it so they can't oxidize in the first place. That might be asking a lot, though. So phthalates themselves, there's questions about whether these are safe things or not, and you'll see certainly ads claiming that they're extremely dangerous, like some of the assignments that we saw. It's used not only in plastics, sometimes these are also used in different perfumes. This is suggesting that they are harmful for developing babies. And then this is another one that kids shouldn't have it in shampoo because it's toxic, et cetera, et cetera. This is just one of the examples of one of the phthalates' chemical structure. So, of course, a lot of testing has been done on phthalates, like has been done on almost every other consumer product. And these are extremely non-toxic. So in terms of toxicity, they're extremely non-toxic. And that's because they have chemical similarity to fats, and our body is full of enzymes that are excellent at breaking down fats. So these phthalates have a half-life in the body of like an hour or between 1 and 2 hours. So they're very, very quickly broken down and excreted. And for that reason, they don't build up in the body. And so it's very, very difficult to get a toxic overdose of these things. However, the worry that is being brought up by many groups isn't necessarily that you're going to get a toxic dose, but that they're so ubiquitous in the environment that you're always exposed to a low dose. Using your pen right now, right? You're holding onto that rubber grip, you're getting phthalates. Phthalates not only are in things that you're coming into contact with, they're so widely used that they're in the dust. So if there's dust and you're coming into contact with dust, you can find phthalates in the dust just because plastic particles are everywhere around us. So these have been and continue to be very highly studied, and there's a number of them that have been deemed to be quite harmful by Health Canada, and those are banned. So there's a handful, I think 3 or 4, that are banned by Health Canada and can't be used anymore. There's a whole lot of variation. This part of the chain can change. And so there are variants which are found to be very low risk, and those ones are still allowed to be used. Vinyl records, these don't look like the vinyl we saw before, right? These have a color to them. They're black. And you can actually get records that are other colors, but mostly they're black. And it's an interesting question why they're black, what makes them black. And you can actually trace this back to a patent number 2,997,451 in the US, filed initially in 1957 to make records black. And what they do in the record is add carbon black. Basically, they're adding charcoal, adding just carbon. We've seen carbon before when we talked about how to purify water. It's this black, powdery substance. Grind it up really fine. Mix it in with the plastic while it's still hot, and you get these black records. So the reason they do this is because PVC itself, as a plastic, is an insulator, which means it doesn't conduct electricity or heat very well at all. And so what happens is as the record turns around on the turntable with the little needle in the groove, that motion of those two materials against each other can generate static electricity. Static electricity can then attract dust, and the motion of the needle in the groove, if it's dusty, can wear down over time the plastic and makes the records kind of wear out and not sound as good and make them less useful. So the purpose of putting the carbon in there, it's not to make the plastic harder or anything like that. What the carbon does is actually make the plastic much more electrically conductive. And it prevents buildup of static electricity, and it prevents the dust from settling as easily on your records. I don't have a record player. I know my parents did when I was a kid, and I think that was like around when they're being phased out. But a lot of record players would have like a cover that would like go on top to prevent dust from getting at the record as it was playing. But this is just another method. So you can take it out. It just means those records probably under normal operating conditions aren't going to last as long if you don't have the carbon in there. Another issue with PVC is what happens if you burn it. And essentially every plastic can be burned. They can, they become carbon dioxide and water like many other hydrocarbons. PVC, though, has that chlorine in there. And chlorine, we've seen a number of times, chlorine can cause problems. We know chlorine as a gas is toxic, which is why we use it to purify water. We know chlorine in the atmosphere will destroy the ozone layer. So that's not good either. You don't want it getting up there. So what about this PVC, this plastic that we're putting tons and tons and tons out every year into the environment that contains chlorine? What can happen to it? Well, if it's sitting there, it's just a piece of plastic on the ground, it'll just sit there and probably not do much at all. It'll slowly leach out any plasticizers that are in it, but other than that, it's not going to really react very quickly. But if you burn PVC, it can create very, very toxic materials, which is not a problem associated with other types of plastic. If you grew up near beaches like I did, and you'd like to go out as a kid even, and all the way up and have bonfires on the beach, there'd always be somebody who would try to throw plastic in the fire. And you'd always say, don't throw plastic in, it makes poisonous gas. That's partly true. It depends on the type of plastic. Right? There's a lot of different types of plastic, and it would depend. So the one that's actually really toxic from PVC is a chemical called a dioxin. And this is a review article published in 2015, Dioxins and Polyvinyl Chloride in Combustion and Fires. This talks about, how the dioxins get produced and then how much based on the type of fire you're using. Now this is potentially an issue because, as I said, there's tons of PVC in the construction of buildings and houses. And if a house catches on fire and burns down and you're exposing all this PVC to very high temperatures, you're going to be generating dioxins and releasing them into the environment. Dioxins were used as in a poisoning, a very, I guess, famous example. There's lots of examples of Russians intentionally poisoning political rivals. And this was one of their rivals, Yushchenko, who was leader of the Ukraine for a while. And he survived a poisoning attempt, and they used tetrachloroparadioxin, which is this chemical here, with 4 chlorines, one here, one here, one here, one here. This compound, tetrachloroparadioxin, is produced when you burn PVC in certain amounts. This is the most toxic chemical that we know of in terms of its LD50. It's the most toxic chemical that is made by human beings. We know it's not the most toxic chemical overall. What one's that? Botox, yeah, botulism toxin. Botulism toxin actually, by weight, is 1,000,000 times more toxic than this one. But this one's still pretty nasty. And so he survived poisoning. This is what he looks like after. You can see how his face is all kind of weird looking. That's a consequence of poisoning by chlorine-containing substances called chloracne, which is a skin disorder. And so he actually managed to survive this, but many others were not so lucky. This is it. Worst dioxin at all. The LD50 is 1 microgram per kilogram of body weight, measured in guinea pigs. I said 1,000,000 times. It's about 1,000 times less toxic than botulism toxin. I think botulism toxin was 1.2 nanograms, which was 1,000 nanograms in a microgram. So still definitely something with a very, very low toxic dose. It is, in addition to being acutely toxic, it's also a group 1 carcinogen, meaning it's known that exposure to this over the long term, so a chronic exposure to this, will increase your risk of developing cancer. Its ADI is super small, acceptable daily intake, 0.7 picograms per kilogram. A picogram, 1 picogram is equal to 10 to the minus 12 grams. So a nanogram is 10 to the minus 9 grams. And a microgram is 10 to the minus 6. A milligram is 10 to the minus 3 grams. So yeah, picogram, super small. This is a paper that was published by a person I went to graduate school with. His name is Sierra Rain. And he did this work. This was a paper that was published very shortly after the Twin Towers came down in New York. So it was 2001, of course, that the towers came down. This was published in 2005. One of the people in this study, what they did is a few days after the World Trade Center the collapses of the two World Trade Centers took place, he went around to various buildings in New York and basically had a whole bunch of little vials, glass vials, and he took these just pieces of plain paper, like we call them CHEM wipes. They're like lab wipes that we use. He would spray it with a little bit of organic solvent, and he would wipe a window with it, and then he'd tuck it into a little glass vial and put it in his case, walk down the street, and do it again somewhere else. So by the end, he had a few hundred of these at various places around New York. He then had each of these little vials tested for how much dioxin there was present in the film on the windows of various buildings. And the result that they found was basically wherever the World Trade Centers were, there were these kind of rings. Well, I guess like there wasn't very many buildings out here, but there were very high concentrations close to the World Trade Center, and as you went further and further away, the concentrations dropped off. So the thinking there was that there was very high temperature fires taking place inside the World Trade Center for, I think, 40 minutes to an hour before the first one collapsed. When they finally came down, it sent up this huge plume of dust, which kind of blew through the city, and some of that was captured on the windows, and they were able to actually see the dioxin plume in New York. And obviously New York is an extremely densely populated place, and there was a lot of people, especially first responders, who developed illnesses after responding to this disaster, which may be, at least in part, attributable to what they might have been breathing in at that time. This is just another one. Vinyl shower curtain, a volatile hazard. Volatile meaning there's substances potentially in the vinyl that can evaporate away. They say there's 100 toxic chemicals. Whenever you see this, though, remember, at what dose? You know, under what conditions are these toxic? Now, if you get a vinyl shower curtain and you open it up out of the package for the first time and hang it, your bathroom smells very strongly of, you know, the vinyl curtain for a week or two before it eventually goes away. I guess my suggestion would be to let the room air out pretty well. Leave the ceiling fan on if you can, or leave the window open. Not that it's going to kill you or anything like that. It's just kind of an unnecessary thing to want to risk. Eventually it'll off gas and should be fine. A few more questions. What rigid plastic has recycling code number 2 and is made up of tightly packed chains with minimal branching? That is high density polyethylene. What is added to PVC to make it soft and pliable? That is phthalates. What is added to PVC in vinyl records to make them more electrically conductive? And the answer to this one is just straight up plain old carbon. Black material to keep the dust off. Number 4, plastic. PETE, polyethyl terephthalate is what this is called. This is, I guess, polyester. And this is often used for clothing. It's used for fabric. Around 60% of it is used to make fabric clothing. So if you have basically any clothing that's not cotton, if it's poly-cotton blend, the poly part is this stuff, or just polyester, or any kind of like, you see this often in workout clothes stuff. It's not spandex, but it's you know, it's that type of material. Around 30% is used to make drink containers. So water bottles, these cheap water bottles, are often made out of this stuff as well. So that's recycling code number 1. And that's our 4th most produced plastic, at an amount of around 30 million metric tons per year. So yeah, we make a lot of this stuff too. This one is kind of an issue as well. We talked about microplastics last time. The problem is with this type of material is when it breaks down, and when I say break down, I just mean like running in your washing machine or running in your dryer, it releases small little fibers that can end up in waterways and oceans and so on, which we call microfibers. And these microfibers are basically microplastics that I guess we're putting probably more of this type of microplastic. It's an important source of microplastic from our own homes because of the way washing machines work. And I guess, like, hypothetically, these could be filtered out, and some waste treatment plants would filter these out, but certainly not always. And the fifth one we're going to talk about, and I think we're only going to talk about the top 5. There's a few other ones we're going to throw on, just give them a mention, is polystyrene, plastic number 5, in terms of 5th most produced plastic in the world. It has recycling code number 6, and we make about 15 million metric tons of this stuff per year. This also goes by the name of Styrofoam. If you take this material and pump gas into it, essentially what you're making here is Styrofoam. If you don't pump gas into it, it makes kind of a material that's semi-rigid. It's very, very cheap. So without putting the air in, here's the plastic I want you to think about. When you buy individual little tubs of yogurt, and they come in like 8 packs, that plastic that is used to make those little tubs is polystyrene. So it's not very strong. It's not very durable. You could probably, bend that container a couple of times and it would crack, and you could probably just rip it apart with your hands. Very kind of cheap, I might say low quality plastic. Polystyrene is one of the ones that is most demonized out of all the plastics. Probably if I was to suggest which one is the worst one for us to be using in terms of environmental impact, I would probably say PVC, but it's not the one that seems to get the worst rap. It's polystyrene. And so you see, things like this. I have some styrofoam cups, so I'm going to show just something in a minute here. We saw this guy last time. Chris Jordan had this artwork showing how much of this stuff we produce. We use styrofoam, a lot of it in shipping to protect. It's very light, so it's cheap to ship things, and it can protect materials either as packing peanuts or as like molded styrofoam to sort of form fit around something that you want to ship and not have it break. This is what they look like up close. So what's the main problem with styrofoam? The main problem with styrofoam is, out of all of the plastics I've talked about, and I just said it's not very durable and strong, and that's true for the materials you make out of them, but it actually is extremely resistant to break down in the environment. It probably has the longest lifetime out in the environment compared to any other plastic that we talked about. It doesn't break down easily at all. And if you took a yogurt container and you buried it in your backyard and came back in like 500 years and took it out, it would probably look identical to when you put it in the ground. It doesn't break down easily at all. However, it has some good things about it too. And it's actually funny, that statement I made saying it never breaks down, never decomposes, you could argue that that's a benefit of the compound, of the plastic. Because when you take plastics and they break down, there's 2 problems associated with plastics breaking down in a landfill or somewhere else. One is they break down into smaller molecules that can then migrate through the soil and potentially contaminate water and other things like that. The second problem is when they ultimately break down all the way, they become CO2, and that CO2 drives global warming. So there's actually a movement in chemistry to try to find ways of taking carbon dioxide and turning it into a solid carbon product, which we call carbon fixation. And if we can fix CO2 into solid carbon permanently, we can lower the CO2 levels in the air. So plastic, styrofoam, is essentially the perfect carbon fixation product because it will never break down again. Of course, that assumes that you're storing it properly, that it's not ending up in oceans, that it's not ending up in the woods and things like that. So clearly litter, you want to break down very rapidly. In the 80s, there was a lot of styrofoam packaging in McDonald's food, for example, or fast food was often in styrofoam. Because one thing about styrofoam, in addition to being cheap, in addition to being light, so it doesn't take a lot of fuel to ship it, it's also a very good insulator. So if you're serving hot food, it's good to put it inside styrofoam because it keeps it hot. But the problem is McDonald's wrappers and things like that are one of the most commonly tossed out of car windows type things, which is obviously terrible. But if people are going to be doing that, you can't stop everyone from doing that. At the very least, you can have them tossing out products that will break down in a year or so, like paper or cardboard, ideally. There was a paper that was published 15 years ago or so from somebody at the University of Victoria who was teaching there while that's where I did my PhD. So I knew this guy. And what he did was what's called an energy audit. And his first sort of claim was that the biggest environmental problem facing us right now is associated with our usage of energy and creation of greenhouse gases like carbon dioxide, also methane. Most of that we produce comes from energy mining. So if you consider our biggest problem being our energy use, it's environmentally friendly for us to reduce our energy usage. So what he did is he compared a bunch of different materials that we might use to store hot drinks like coffee or tea. He looked at a ceramic mug, which is what you see here. This is a plastic mug, solid, hard plastic mug. This would be a glass mug. This would be like a cardboard, like a paper cup versus styrofoam cups. And styrofoam cups have kind of fallen out of favor. You don't really see these. In fact, I can't think of any store or like coffee shop that would serve in styrofoam anymore. At the time, though, it was the go-to, like in the 80s, because it's cheap and it's really good at keeping hot beverages hot. And so what he looked at was the energy required to produce each one of these and which is the most energy efficient cup to drink your coffee or tea out of. And looked at the weight of the different cups, looked at the materials, the energy required to produce that material, and then how much so-called embodied energy there was. And what he found is the styrofoam had way less. It took way less energy to create the cup than it did something like ceramic. And so what he was able to say is that in order for the energy cost for the styrofoam cup to equal out with the energy cost of producing the ceramic mug, you would have to and by the way, with the styrofoam cup, the idea is you use the cup and then you throw it away. You only use it a single time, where the ceramic cup you can use again and again and again. So the idea is yeah, it costs a lot more energy to produce the mug, but you get to reuse it many, many times. So it turns out you'd have to reuse the ceramic mug around 100 times in order for the energy cost of the ceramic mug to equal the styrofoam cup. And you might think, yeah, that doesn't sound unreasonable, right? You buy a pack of 6 mugs, you could use them for years and years and years. That assumption, though, assumes that you never wash the mug. Because washing a mug requires energy in the form of hot water, of soap, things like that. And it works out that if you wash your mug, even every couple of times, you'll never break even. So buying a ceramic mug and washing it after each use requires a lot more energy than using styrofoam and throwing them out each time. And so his claim is that styrofoam itself isn't bad. The issue is with the garbage collection. Because he said if you collect all of these once they've had their single use, you can then burn them and get the energy back out of them. So it's like taking oil and burning it for energy. Well, it makes more sense to take the oil, turn it into a cup, and then collect the cup and then burn it for energy afterwards. So you still get all the energy out of you would have anyway, plus you get this use, and you get to avoid using ceramic, which costs the environment that way. So it's an interesting perspective in that, we think plastics like styrofoam are bad because they are a garbage problem. They don't break down, they don't decompose, and they can end up as litter, and they end up in the ocean and so on. But compared to alternatives like glass or ceramic or something like that, there's also a lot of benefits to using plastics in certain situations. Now, the problem is you could never, I don't think, start replacing every reusable cup with disposable cups and expect to collect 100% of them, right? But in a theoretical model like this, it does save you energy. I'm going to show you just a quick demo, actually. This is a very short one. I'm going to switch my video, and if you're sitting over there, you may want to come over here if you want to see it. Let me just move my camera over to here. And so what I have here is some styrofoam cups. Let me be safe and use my safety glasses here. And what I have is chemical solvent. It's acetone. It's basically pure nail polish remover. And this is pretty, it's not very polar. It's not polar like water is. It's pretty non-polar. And this can dissolve many plastics. And plastics are very non-polar typically as well. This one is polystyrene, as I'm sure you're aware. And what we can do actually is, you can hear this. If you squirt a little bit of polystyrene on there, acetone on there, what you can start to see, well, I don't know if you can see that at all in the video. It's kind of starting to pour a little more in there. You can see this starts to dissolve away. It breaks down. And non-polar plastics will dissolve quite well in fairly non-polar solvents. What I'm going to do is ramp this up a little bit. Pour some acetone in there. I'm going to show you that you can basically take like a whole stack of these things and push down on it. And dissolve this away pretty well. And what's interesting is, like, when you're all done with this, the big decrease in volume you see going from the initial material. So you can take a large volume of styrofoam and it all kind of crunches down into a very, very small amount. And it depends exactly. This styrofoam is actually fairly dense styrofoam. And you can get styrofoam that's used like to package electronics. And you can get like this great big brick and it just goes like basically down into nothing. Spray this down a little bit more. And it's a nice demo, I think, of how much of styrofoam is actually just empty air. And we kind of think of it maybe as a solid material, but it's actually like, I don't know, by volume, probably 95% at least air. There's actually another demo, which I've actually never tried because I don't have the equipment for it. But what you do is you take a container and you put a bunch of packing peanuts in it, and then you put it under really high vacuum for 10 minutes or something like that. And what happens is a lot of the air that's trapped in the plastic actually will come out and get pulled away because of the vacuum. And then what you do is you let the air back in, but you don't just use air, you use helium. And then what will happen is the helium will go into the little holes in place of where the air was. And then when you take the top off, they all fly up. And the nice thing about that demo is they'll stay up there until slowly the helium will come out and get replaced by air. And it happens over the course of like days and weeks. And so like, if you did it in a classroom, just every once in a while, a random packing peanut would fly down from the ceiling. So they'd probably be upset with me if I did that in this room. But it sounds like fun anyway. So anyway, we get this. I wonder if I have something I can use to show you what it looks like. Even like a pen or something like that would work. Let me dig in here and see what I can find. What do I have? Found something. So what I'm going to do is just bring this close to the camera too, so hopefully you can see. It makes this really kind of goopy material. And this is just, you know, if you pull it, you get these really long kind of stringy strands, almost like melted cheese. And it's because this is a polymer. It's made out of really long strands. You get this little kind of like thick ball of dissolved polystyrene. And this, if you leave it dry, eventually what will happen is all the acetone will evaporate away. And this stuff will become like rock hard, very, very hard and brittle. And if you hit it with a hammer, it would crack, it would shatter. Even though now it looks like kind of like a gummy kind of material, it actually becomes like a very, very hard stuff. It makes cleanup easy for this demo too. That liquid will probably evaporate before the end of the class. Actually, you could probably like mold this into a shape if you wanted to. Let it dry, and then you'd have a hard plastic, whatever your shape was that you wanted. Cool. All right, we've got a few more plastics we wanted to talk about. Teflon is one. Teflon is a very ubiquitous one. I'm sure everyone's heard of it and everyone's probably used it and come into contact with it. Teflon is not one of the top 5 or 6 by mass. Like, we don't typically make a lot of disposable things out of Teflon, so that's what keeps it from being one of the big boys. But we use a molecule, it's like ethylene with all the hydrogens replaced with fluorine, and it makes, again, polyethylene, long chain, just like polyethylene, except fluorine's in place of all the hydrogens. So it's PTFE, polytetrafluoroethylene is what the PTFE stands for. The nice thing about Teflon is it's probably the most chemically resistant and chemically unreactive and inert plastic that we know of, or material that we know of. So it's one of these things, it's one of these go-to substances in chemistry that if we have some type of reactive material that eats through plastic or eats through glass or eats through whatever, so the first thing is always like, well, let's try Teflon. Maybe it won't eat through Teflon. And generally speaking, it won't. It's actually accidentally developed in 1938. I think they tried to purify tetrafluoroethylene in a cylinder. They filled the cylinder with this pressurized gas, and they came back and the pressure went down to 0 overnight. And they cut the tank apart, and they found this big solid block of Teflon inside. The reason I have this gecko, if you've ever traveled somewhere warm, there's geckos sometimes you find on the walls. Teflon was the first substance found that geckos could not walk on. That they can like walk upside down on almost any substance and stick to surfaces. But Teflon is so non-stick, so unsticky, that these things weren't able to even walk on a wall made out of Teflon. So you find a lot of Teflon coating pans or cookware for both reasons. It's chemically inert, so it won't, you know, react with the material you're cooking with, and it also prevents it from sticking, makes things non-stick. Problem with non-stick, though, of course, is the Teflon has to stick to the pan somehow. And they have a set of compounds they use to stick the Teflon to the pan, and they're called PFOAs, polyfluorooctanoic acid. And there's a family of these types of similar compounds. And there's some concern over those, because those are extremely long-lived in the environment as well. Environmental problems with almost any chemical substance comes down to 2 factors. One is, you know, their chemical activity, their toxicity to certain target species or whatever. And the second one is how long they last in the environment. So if you put something out in the environment that is extremely toxic and damaging, but decays in a day, it's generally not going to be that dangerous, right? Unless you happen to be right in its path on day 1, of course. What polymer is used to make styrofoam cups and packing peanuts? Polystyrene, which is where the styro and polystyrene styrofoam comes from. What's the primary environmental issue associated with polystyrene? it degrades extremely slowly, creating a persistent litter garbage problem, right? This would not be a problem if we could collect it all and didn't let it get out into the environment. Except, I guess, you fill up landfills. But it doesn't leach, so it's good. It's a good material, I guess, to put in a landfill. The last little piece that I wanted to talk about in this unit isn't about sort of cheap products that we make out of plastics. It's sort of advanced plastics. It's advanced materials that are polymers as well that we use. Most plastics, as I said, are insulators, and this is the issue with vinyl records, is that they develop static electricity as a result. In fact, if you look at wires, they're often coated in plastic, and that's because they insulate, they don't conduct electricity. So if there's electricity running through the wire and it's coated in plastic, you can touch the plastic and the electricity won't shock you. And it isolates, if you have bundles of wires, electricity won't cross from one wire to the other. However, in 1976, it was discovered that they could make a plastic that did conduct electricity. It's this particular polymer called polyacetylene, where it's like this is the repeating subunit here. I guess it's just, I guess even just this much is repeating. This material, if you expose it to gas phase iodine, makes a very conductive material, a material that conducts electricity just as well as copper. And this got people really excited because they believed that polymers couldn't conduct electricity, that they're all insulators. And one of the problems with metals as conductors is that they're difficult to process. And when I say they're difficult to process, what I mean is you got to heat them to very high temperatures to melt them, to turn them into wires, which means, you have to make them under certain conditions. Also, metals are fairly scarce, they're expensive, and they're heavy, they're dense, and these are all practical challenges with using this. And when I say the high temperature, why that's a problem is if you're trying to make like circuits or microprocessors or things like that containing copper, it adds a production challenge if you have to heat the copper to a very high temperature in the presence of silicon or plastic other parts and things like this. So the hope is that they could develop plastics to replace metal wires, which would make it much, much easier to potentially make cheap, disposable electronic items and goods. It's been a lot of work, actually, to do this. Nobel Prize was handed in 2000. We still don't, there are examples of polymers that do conduct electricity very well, but none that are really widely deployed. There's some interesting applications, like there's one thing about polymers is many polymers will dissolve in certain solvents, like we just saw with our styrofoam and acetone. And so what that means is you could actually put a polymer into a printer ink cartridge, and you could design a circuit on a piece of paper or on a computer and then print it out on a piece of paper, and wherever the ink would be a conductive, basically, wire on the paper. And you could connect your paper with alligator clips to a battery, and you could have like a functioning circuit printed out that way. That's what I mean, it's easy to process. You don't need, like, to do that with copper, you have to heat it up to however many 100 degrees to melt the copper first. You can't do something like that. OLEDs are another, and this is interesting. When I was in grad school, I was following there was a lot of people working on trying to create polymers that when you conductive polymers that when you put electricity through them would glow. And it was interesting for me because when I got interested in this, probably around the year 2000, they were very good at making emitters that were red and emitters that were green, but they needed the third one, which was blue, to have the full RGB for a display. And at that time, they had a lot of technical issues developing a compound that could emit blue, but was also stable, long enough to put into a device like a TV. So they've fixed that problem, they've mastered it, the chemical research panned out, and they now have displays which are organic light-emitting diodes. And the way an organic light-emitting diode works, it doesn't show it here, is basically you have a layer of, it's a conductive glass called indium tin oxide, and then you have this polymer layer, and then on the back you have a metal. And what you can do is connect those two and put a voltage across, and you can have electricity flow through the plastic material. And when it goes through the plastic, it excites the plastic and makes the plastic glow. So this gives off light. And you'd make one that would give off blue, one that would give off green, or one that would give off red. And this actually requires way less electricity to produce a display than other methods. Because the other method that's often used today is called just an LED. And what an LED does is it has a light, and then it has what's called a liquid crystal. And basically there's basically a switch. This is almost like a Venetian blind, where you can put a voltage, open it, and let the light through, or you can take the voltage out, it closes, and the light won't go through anymore. It uses chemicals called liquid crystals. The problem with this is even when the pixel is off, some light will kind of go through a little bit, so it's not perfectly black. Whereas this one, the OLED, when it's off, is perfectly black. And so what that allows you to do is create a display with better contrast. Also, this one is sucking energy even when it's off, right? When that pixel is off, the light behind it is still on. It's just off because you've closed the gates, if you will. So the light is in there, it's just being absorbed, and that generates heat in the device, and it also consumes energy even when those pixels are off. This only consumes electricity when that pixel is on at that particular point in time. So OLEDs are what's used in the highest end iPhone screens now. So if you have like the iPhone Pro, they're OLEDs. And I think if you have the regular one, at least with the 11s, iPhone 11, the regular iPhone 11 did not have OLEDs. The advantage of OLEDs in your phone, first of all, is you have better contrast, because the blacks are truly black because there's zero light coming from them, where the LED backlit ones do have light coming through. And the other is because they're more energy efficient. That's a big deal in a device like an iPhone, because it means your battery is going to last a lot longer. So that's the main advantage from my perspective on having an OLED in a device like a phone, is that the battery, you can get more hours out of your battery before requiring a charge. So these have become pretty mainstream now. You can get full TVs that are OLED displays, certainly lots of small devices. I remember like 15 years ago, the first OLED devices were coming out, and they were car stereos, the little panels for car stereos, and they typically only had one color, which was red for the writing. And that's because red was the first one they were able to develop, and it was much later before the blues could come out where you could have a full color display. So this is why they claim they're good. Perfect black, because there's no backlight. Wide viewing angle is another one, because the pixel is like a little individual light bulb that's on, as opposed to the light in the back going through the pixel. They're sort of more designed for being face on in front of the TV. So if you're at an angle, you don't get as much light, where OLEDs don't have that problem. All right, another type of, I guess, higher tech plastic that's coming out right now are what are called bioplastics. And these are plastics which are designed to biodegrade. And this would solve the main problem associated with disposable plastic, which is garbage and litter, ending up in the oceans and ending up in organisms, marine organisms and things like that. So the idea is if you could take a biological material, such as cornstarch, which is renewable to begin with, because you can grow corn as much as you like, modify it to make synthetic plastics, and end up with a product that if you bury it in your backyard will be gone in a year. That would be considered, I guess, a win. And so there's a lot of research that is going into this, and there's already products commercially available that you can get. I know back when campus had food service at different places, those little coffee kiosks, they had a lot of this type of material. It's called plastarch material, or PSM, and sometimes just called corn plastic, where this was biodegradable. And so you could pay extra if you're a food delivery type place and use these types of plastic products, which the litter problem associated with these are greatly reduced. It's interesting though, we say everything has pros and cons. What are the pros and cons of using something like this? Does this just solve all problems that we have now with plastic? And the answer is probably no. First, they only reduce fossil fuel use by a little bit, 20 to 40% maybe under ideal circumstances, because it takes a lot of energy to grow corn and to harvest corn and then convert corn into plastic. So even though corn derives its energy from the sun as it's growing, it doesn't mean that it doesn't require some energy to produce it in the first place. Not only does corn produce or require some energy, it also requires land. So if you have to cut down forest to expose more land to grow more corn to then convert into plastic, is that getting you any further ahead? If you could find a waste product you could turn into one, that would be fantastic. When they decompose, they release greenhouse gas, of course, like any biological material. Is that a major concern? Well, it's probably not a hugely important source of CO2, but it is a source. It becomes competition for corn growth. And this is actually a big problem now with people that are trying to use corn to make fuel. Because you can take corn, turn it into ethanol, and put ethanol, mix it with gasoline, and make a type of fuel called E85, which is 85% ethanol, 15% gasoline. And there's cars that have engines that will run on this, and there's various places you can get it. Problem is this increases the demand for corn. This raises the cost of corn, and certainly in places with maybe worse food security than Wolfville, raising the price of a staple food is not a very advisable thing to do. And there's a lot of people that will say we shouldn't be using our food as an energy source. We should be using our food as food, and we use something else as an energy source, like wind or like solar or like these other energy sources that we have that do not impact our food supply. Interesting way to think. We have one last question before we finish up this unit. Which polymer type below do you expect to be most water soluble? Polyvinyl alcohol we didn't talk about much at all. Polypropylene we did though. This was number 2 if you remember. Polyethylene was number 1. By number 1 here I mean in terms of production, not the recycling code. PVC, which was number 3. Polyacrylonitrile, we haven't really talked about too much at all. The answer here, what should we be looking for? What makes something water soluble? Hydrogen bonds. So something with OHs and NHs, which polyvinyl alcohol has several of. So polyvinyl alcohol is water soluble. Polyvinyl alcohol is what you find, it's used in glue. So glue is like a solution of water and PVA. And when you mix them together, you get this paste, right? And then if you spread it on 2 pieces of paper and smush them together, when the water dries out, you have this sort of hard plastic substance that's left over, which you could wet again and it'll dissolve again and you could, re-wet it. But yeah, so that is what makes it water soluble. When you think of plastic, you don't think of water soluble, right? You think of plastic, you throw it in the ocean, it's going to float wherever. It's not going to last. But PVA will dissolve in water. And if things dissolve in water, they typically break down quick because it makes it easy for microorganisms to then decompose them. So polyvinyl alcohol is not really much of an environmental issue because it's water soluble and can be dealt with quite easily. Perfect. So we are done with this particular unit. What that means is our unit assignment will be due 7 days from today, next Thursday, which happens to be April 1st, which also happens to be the day that your assignment 2s are also due. It's due day for everything. But if you're following along with me, you should be already done this assignment anyway, in which case we won't have an issue. So thank you very much, everybody who's here, not just in person, but online as well. And we will see everybody next week.